the resolver. This laboratory experiment demonstrates principle of the resolver. Here is some source of about 7 MHz. This coil represents for the router, and this is one of the stator winding. If we have second stator winding, it will be in this position. And now I can show you that if I place it here, there is some unwanted signal, some noise. But except the noise, you can see that, yes, in this case, the signal has the same polarity, source and resulting signal. If I turn it opposite, it now has opposite polarity. This goes down, this up. In this case, it's just 90 degrees turned, so there is nearly no signal except the noise. So dependency of the mild signal on turning depends on sinus of the angle. For the second winding, it will be cosinus. So the same principle is used for resolver to measure the position of the rotor inside the two stator coils. We will show it on our real equipment in our laboratory. Industrial version of resolver. On our preparation, we have a resolver standard with 2 windings and rotor. As a power source is here internal power source of this old oscilloscope, which can be set to any frequency from 1 Hz to about 9 MHz. Now it's switched exactly to 10 kHz. This is used as a synchronization, so we have stable picture. And this is source, and we have 2 windings on first and second channel of the oscilloscope. So you can see there is X winding and Y winding. The second one is emphasized by triplet curve. If I turn the resolver, it will change its shape, but you can see that it's still the same frequency. This is the same polarity, this is negative polarity, both negative, first again positive, both positive. So the amplitude of each of these 2 curves represents sinus and cosinus of the angle, and from the ratio of first and second you can evaluate exactly the angle. So for the solution of this problem, if you need real evaluation, you can use special integrated circuit, resolver digital converter. We don't have it here because we just need to demonstrate the principle. The task for this exercise is to measure in some step, probably 30 degrees, the amplitude of one or both signals and draw it in some range to a graph, this dependency. We have measured data from previous years of study, so this is task for this exercises. Position or length measurement or dimension measurement using ultrasonic method. So we have some source of sound which goes through our environment, reflects here, goes back, and it's received. So we can measure time of this trajectory, and we can evaluate length of this dimension by evaluating time divided by 2 and speed of sound in this material. In this case, probably in air. In the air, the speed of sound can be evaluated using this equation. So it's pressure, density, and Poisson's constant. We can rewrite it to standard gas formula equation, and here it's visible that this is constant and this is temperature. So the ratio between pressure and density for the air is dependent only on type of the gas and thermodynamic temperature. So higher temperature, higher speed of sound. The same equation works, works for steel. Here is Young modulus density, but it's true only if you have only one-dimensional metal. For example, in this case, we have 2 cans from their bottoms connected by long wire, possible steel or some copper wire. And if you tell anything to this can, it will be transduced through the wire and you can listen it here. It's a good example as wire phone, very old mechanical phone. But the speed is not same if you have full material where the waves have to spread to all dimensions. In this case, the speed of sound is very complex, and we will probably calibrate our devices using some example of thickness. For the steel, another important thing is that the air between the sound and the material can't transmit energy into metal. So here should be some medium which will transfer the sound, a typical white grease. We will try to measure thickness, measurement for measuring thickness of steel in our laboratory. Ultrasonic thickness measuring set. In this component, it's a power source. Main part is the sound, which contains transmitter and receiver, in this case separated. It works on the frequency of 10 MHz and ultrasonic thickness gauge. Important is this example of thickness, sample of thickness of 5 millimeters. Now we should go to many and set exactly 5 millimeters of thickness. This is calibration for steel. Now we can measure some experiment. For demonstration of possibilities of this measuring device, I have few samples. For example, here we have 2 thickness. For transmitting waves, ultrasonic waves into material, we need some grease. The thicker part, the thinner one, and you can find where is the place where it's changed. Sorry. It can be used for measuring samples which are hollow. There is hollow inside, and we have different thickness of each wall. So I can measure 3 of them. This and this should be same, and this could be different. Is it different? This profile has 3 millimeters thickness of the wall. This is even a little thicker. This is piece of sheet, and this side has nearly 80 millimeters. So we can measure the thickness of the wall of closed samples. Some example, some very thin bar, and here we have tube. The tube has different thickness of wall on this side and this side. So we can measure 2 of them, position. The thicker one, 3.4, the thinner one, 2.8. You will solve the problem of drawing the dependency of thickness on this scale. So we will prepare a table with data for each centimeter on perimeter of this tube, and you will evaluate the graph. That's everything from this measurement. Ultrasonic parking sensor. It's used as a device in car to detect any obstruction if you like to park somewhere. It contains some display unit, evaluating device, and 4 sensors. We have only 1 sensor. It works on 44 kHz. It produces signal on its own frequency and detects it when it returns. So we can try it. And you can see that distance lower than about 30 centimeters can be detected. It's because in these times there is still residual frequency vibration from the produced wave, so it should become quiet before it can listen. So for cars, you can detect last 30 centimeters or 40, it depends on device. Maximum range depends on quality of this obstruction. If you have something like a bush or some fabric, you can detect it for short distance. That's all as a demonstration.